So now I have a full example for a repeated measures ANOVA. Remember that a repeated measures ANOVA has one factor with at least two dependent levels. By saying that the levels are dependent, it means that they share variability in some way, that they have some kind of relationship to one another. Now, the repeated measures ANOVA is almost identical to the one-way ANOVA, except for one additional calculation we must perform in order to account for this shared variability. So it's going to be almost the same as the one-way with just a few changes. Now, here is my example. Researchers want to test a new anti-anxiety medication. They measure the anxiety of 7 participants 3 times. Once before taking the medication, once 1 week after taking the medication, and once 2 weeks after taking the medication. Anxiety is then rated on a scale of 1 to 10, with 10 being high and 1 being low. Are there any differences between the 3 conditions using an alpha level of 0.05? And here is our data. You can see that we are measuring the same 7 people 3 times. That's why this is dependent data instead of independent data. And this is why we're doing a repeated measures ANOVA. So this repeated measures ANOVA has 7 steps. We're going to state the hypotheses, state the alpha, calculate the degrees of freedom, state the decision rule, find the test statistic, and then state our results and conclusion. So let's start with step 1, defining the hypotheses. Our null hypothesis is that all 3 groups will be equal, that before week 1 and week 2 will be equal to one another. And H1 is that not all groups will be equal, that there will be a difference somewhere among the groups. Stating alpha. Alpha, I said to use 0.05, and you're going to use whatever, usually 0.05 or 0.01 or something like that. Here it's 0.05. Next, calculating the degrees of freedom. Well, there are 5 degrees of freedom we can really calculate here. We can find for between, within, subjects, error, and total. Now, first of all, there are 2 things you need to know, capital N and S. S refers to the number of subjects within each level. So we have 7 subjects in before, we have 7 in week 1, we have 7 in week 2. So S is 7. N refers to the total number of measurements you've taken. We've measured these 7 people 3 times, so we have 21 total measurements. Now we're going to use this information to calculate degrees of freedom. So these are the equations for degrees of freedom. We have N, A, S, and 1. A refers to the number of levels you have. So in this case, A is 3. Your teacher might have it as K or something like that, but A and K, they're the same thing. In this case, it's 3. So I can find between, within, subjects, and total. Between is 2, within is 18, subjects is 6, and total is 20. And now that I know all these things, I can find error. Error is 12. So next we need to state our decision rule. And in order to do that, in order to look up the critical value, we need to use 2 different degrees of freedom. We're going to use degrees of freedom between and degrees of freedom error. We're going to use 2 and 12. So I'm going to go to my big F table that has the between groups on the top and the within groups on the left side. And I'm going to look up 2 and 12, which gives me a critical value of 3.8853. That means that if F is greater than 3.8853, we will reject the null hypothesis. That is our decision rule. Next, we're actually going to calculate the F. We're going to calculate the test statistic. So let me organize things in this table here. We're going to need to fill out this table with the goal of finding F. Note that this looks like a one-way ANOVA table. It still has between, within, and total, except now within is split into subjects and error, because some of the within subjects variability is consistent within subjects, and some of it is just due to random error. Because we're measuring the same people multiple times, we can now split that up into those 2 groups and account for it. So I'm going to put in the degrees of freedom that we already know, 2, 18, 6, 12, and 20. Notice that degrees of freedom between plus degrees of freedom within is still equal to degrees of freedom total. Also notice that degrees of freedom subjects and degrees of freedom error is equal to degrees of freedom within, because that's just a subset of that. So now we just need to find the sum of squares for each of those. We're going to need to find sum of squares for between, within, subjects, error, and total. So let's start doing that. First with sum of squares between. This is the equation for sum of squares between. And the top part looks kind of complicated. AI squared. What that means is that you're going to take the sum of each level, square it, and then add together all those numbers. It's easier for me to show you what that is instead of tell you. So that's what I'm going to do here. what we're going to do is find the sum for each of the groups, the before group, the week 1 group, and the week 2 group. So we get 57, 47, and 21. What we're going to do is square each of those values and then add them all together. That's what that top part of the equation means. Now, the t in this equation is referring to the total sum of all the scores. We have to add together all the scores, add together 57, 47, and 21, or add together all the individual scores, and we get 125. And we already know S and capital N because we found them before. They're just 21 and 7. So now we have everything we need to calculate sum of squares between, which in this case is 98.67. Next we have sum of squares within, which is the sum of all y squared minus this thing that we've already found. So it shouldn't be too bad, we just have to find the sum of all y squared. And this is how we do it. We take every individual value we have, square them, and then add them together. So our sum of y squared is 853, and we just put that in there. Now the second part of the equation, we already found it when we were calculating sum of squares between, so I'm just going to put that there. And now we can find sum of squares within, which is 10.29. Next we have sum of squares subjects, which uses both parts that we've already found so far. But we do have this a little bit different. Sorry, I made a mistake there. The first part's a little bit different. What we have to do is sum up the scores for each subject, then square them, then add them together. So that's what I'm showing you right now. We're finding the sums for each of the 7 subjects. We have 20, 17, 15, 18, 20, 19, and 16. So the top part of that equation is we're going to square each of those values and then add them together. And then the rest is stuff we already know. We already know that t is 125, we know that a is 3, and we know that capital N is 21. So now that we know all those things, we can solve for sum of squares subjects, which in this case is 7.62. So far we have found sum of squares between, sum of squares within, and sum of squares subjects. Now we're kind of going to take a shortcut to find these last 2 parts so we don't have to work through a whole lot of stuff. Now sum of squares error is equal to sum of squares within minus sum of squares subjects. So we can just take 10.29 minus 7.62 and get 2.67. And now the total is just sum of squares between plus sum of squares within. So we add together 98.67 and 10.29 and we get 108.96. So now we have all 5 sum of squares that we need. Now in order to calculate the f that we need to find mean squared between and mean squared error. Mean squared between is just sum of squares between divided by degrees of freedom between, 98.67 divided by 2, and we get 49.34. Now mean squared error is just sum of squares error divided by degrees of freedom error, or 2.67 divided by 12, and that's 0.22. So now we have those 2 things, and we just have to plug them into the f equation like that. So when I divide 49.34 and 0.22, I get an f of 224.27. So remember, our decision rule was, if f is greater than 3.8853, reject the null hypothesis. We found an f of 224.27, so we're definitely going to reject the null hypothesis. Our conclusion, what this actually means, is that the 3 conditions differed significantly on anxiety level. When f212 equals 224.27, p less than 0.05. That's the official way of writing it. What this basically means is that there is a difference between these 3 groups. We don't know specifically where that difference is. We would do post hoc tests to find that, but we do know that there is a difference somewhere between before week 1 and week 2. And that is a repeated measures, ANOVA.